Good morning, Year 13. This is the last of the nuclear physics chapters, and this is the one that is the main reason for all of nuclear instability. It's all about energy, so I've retitled the topic, but it's all about this idea of what's going on, what causes nuclear processes to happen. So we're going to look at fusion and fission. We've already looked a little bit at fusion through the astrophysics topic. We're not really going to go much beyond the GCSE kind of way of thinking about things. However, what we're going to look at is the mathematics of it, how he makes it all happen, and just putting the bits and pieces together. So the first bit is the maths, but it's not tricky. It's just being very systematic. So let's just jump into that first bit. This is all coming from Einstein's work in the first place. It does bring us into things, I haven't got it in the notes, but it brings us back into ideas that we've already looked at. It brings us into the binding energy, and it brings us into that bit of a deeper little piece behind everything, and one of the most important graphs to do with the nucleus and atoms in general. Okay, so interesting idea to start with. If we take ourselves a nucleus, and one of the most stable ones is helium. The reason it's so stable is there is a very strong bonding between each of the nucleons in the nucleus. Okay, so we've got our two protons, red in this example. They're trying to repel, so they perhaps have a slightly larger separation. But it's all very fluid, and every single part of these is holding the nucleus together. Now, when you have forces, you of course have energy, because work done. Okay, so if we were to put these together, we would need to come in with a great deal of speed so that we have enough energy to fight against the forces of repulsion. We are not at that stage. We're usually working backwards, so once they've been put together, they, rather like elastic bands, hold the nucleus together. And when we try and pull it apart, when we try and do some work linking in with that graph, mainly thinking about the nuclear strong force, we are fighting against that force to bring it apart. Okay, and it's that means that we need energy to do it. However, when we look at the mathematics of it in a second, we come up with the odd fact that actually when we put these together rather than four separate nucleons, the mass is changed. So the mass of an alpha particle, the mass of a helium nucleus, is less than the separate parts on their own. And that difference is actually due to this idea that came from Einstein's big equation, which everyone knows about, where mass and energy are conversant with each other. Okay, they're transferable. You can swap them. You can think of them as the same thing. So we're going to talk a lot about the rest mass energy, often given the little zero, because it's the fundamental idea of mass for these particles, and the energy contained within that. So we're going to do the mathematics of it. I have conveniently put some data in here, and just remind you that we have this data in the data book. So we have the rest mass energy of various particles, including the alpha particle. So that reason alone gives you a bit of a hint that rather than talking about them separately, they'll often talk about the alpha particle. Okay, why? Links in with a lot of questions on radioactivity, of course, but also it's an incredibly stable particle, and we're going to look at why on that. So the crucial bit is, this is the point where we go beyond that third significant figure. Okay, so up to this point, we've just said protons and neutrons are about the same. That's good enough. Well, we need to go a bit further. Okay, And if we go more than 4 significant figures, we'll actually start to get obviously a better answer, but we actually start to see more coming out of our calculations. Now, they may do this when they give you questions. They may give you values not in here. They may give you the values in terms of a more convenient unit, which is the unified mass unit. Okay, and conveniently it links in with energy, so in some exam boards they will use that as well, but for us we will just do the full proper version, which is E equals mc squared. However, I've given you them in terms of mass unit, unified mass unit, the value of 1/12 of carbon 12. Okay, and when we look at that, we start going further down, we can start to see there's actually quite a big difference between them. Okay, makes it much more obvious. However, for us, we're going to use the data out of the data book. So just bring that back nice and with inside. So if we get our chemists who then do some work, they know the mass of all these particles, okay, the particles that are elemental and of course compounds, but the mass of the nucleus, notice the nucleus we're talking about here, is made up of obviously just the protons and neutrons, but if we add them up, it doesn't add up to that. Now, please note again, in terms of the exam, when we're talking about this mass, change in mass, then we're not going to include the electrons. Okay, those electrons aren't bound with the same forces. They go flying off into the distance. It's not going to make any difference to the actual process. We're talking about nuclear energy here, so it's just the nucleus. So if we just do this, and again try and be systematic when we're doing it, if we add up the mass of the separate nucleons, well, we've got two lots of, let's do protons first, so that's 1.673 times 10 to the minus 27, okay, plus 2 times neutron mass, which is going to be slightly more massive because it can split into a proton, so back to our whole idea there, 1.675 times 10 to the minus 27. For those that are thinking ahead, of course, protons can decay into neutrons. The math still works the same. The idea of binding energy still works the same. So the energy binding it together can be found out using this. We'll come back to the binding energy itself. If we add those up, we end up with 6.696 times 10 to the minus 27. Okay. It's not the same. It's not a lot different, but it's not the same. And importantly, you have to go to more significant figures to make this work, because otherwise the numbers will disappear. Okay, you won't be able to calculate anything meaningful. Let's have a look at that. So I'll just put that NB 4 sig fig. Okay. Now, if we look for something called the mass defect, okay, it's not deficit, it's the mass defect. It's the difference in the mass of the nucleus and the nucleons. Now, it doesn't matter too much for this level whether you subtract, which way around you subtract it. This will always be smaller, okay, this will be bigger, the separate parts will be bigger. I'm not too worried about that. Okay, so if we put that in, we're going to end up with 6.696, and I'm going to keep, because it's the same multiplying factor, I'm going to keep that out. So 6.648 times 10 to the minus 27. That's going to equal a fairly small number, and that is why times 10 to the minus 27, there we go. That's now only 2 significant figures. That's why you have to have more numbers in the original calculation, because we are looking at really small values. So this, okay, as I say, if you were to do this in terms of these numbers, it will make it much easier, because you could just literally subtract them much more easily. You don't need the multiplying factors, you're less likely to go wrong. So often in real physics I tend to use it in terms of the unified mass unit. However, which makes it convenient, and with my calculation, as I said, I've written on my data book, you can immediately convert that into electron volts of energy, or mega electron volts, because nuclear energy is big. But the idea is that we can then just kind of use that idea of mass defect to work out energy. Now this may look tiny, okay, but that is one nucleus. That is the glue binding the nucleus together that has now been converted into energy if we use Einstein's equation. Okay, so there's our mass defect. Okay, rather than the mass of the particle, it's the mass defect, it's the change in mass of the nucleus. We still have got the same particles, they're just separated. Now, quick heads up, the bigger the particle, okay, the bigger the nucleus, the more blue tack in my model holding it together, the more mass defect you're going to get. So the bigger the nucleus that falls apart, the more energy you're going to release. So when we're talking about things like nuclear power and power stations, we want something that A, conveniently falls apart, which we'll look into more depth with, but also is big, is massive, because that will release more mass and therefore create more energy. To give this some sort of context, helium, hydrogen, process going on in the sun, that may look like a small change in energy. Sorry, I'll put a unit to make that really clear. Really small amount of energy. The sun is converting around about 3,000 tons of energy, 3,000 tons of mass into energy every second. The sun is losing about 3,000 tons per second. That's a lot of energy being released from a lot of individual atoms within it, or the nuclei of atoms within it. Okay, so that process on an individual scale is tiny, but it very rapidly can be increased if we have a large enough mass making this happen. Okay, what does this energy look like? Well, again, don't fall into the trap of going, oh, heat, what's that about? No, these are particles that were together. There we go. And if those particles are then split apart, well, they're going to shoot off with kinetic energy. Okay, so the vast majority of energy, all of the energy being released is coming out from that original store as kinetic energy. So our electrostatic, or the nuclear strong force store, giving us our energy, is then released as kinetic energy. Now, if we have other processes, to link back to what we did last chapter, if we have, for example, proton decay releasing, a natural process rather than some sort of forcing this all apart, but if we have an alpha particle falls off, it's just like this, but the binding to the rest of the nucleus has gone. So a large nucleus, helium nuclei dropping off, our alpha particle, that's going to shoot off in one direction. The binding energy that has come out from here will be released. However, if we have a neutron or a proton and it decays, well, again, we're going to end up with our neutrino, an electron, whichever way round. Let's say that's a plus, a positron, that will be a neutrino, or it could be an electron, an anti-neutrino, depending on what decays. In this case, this is of course positive coming out, so this is a proton that has decayed. So in that process, again, kinetic energy, some of the energy taken by that, but then the energy comes and gets involved with pair creation because of the energy, the proton, positron from the proton meeting an electron and giving out energy. So lots of processes can run from this, but the bottom idea is they're all coming out with speed. Okay, so just don't get confused. It's really straightforward, just particles moving. So that store of energy that we call binding energy, okay, the energy that binds it together, hence the name, that is then converted into kinetic. Okay, so let's just put that into transferred, a magically vague word, into kinetic. Okay, by the work done, etc., etc. So when we get to this, then what happens to that energy itself? Well, we can start to map it. We can map it for all of the particles that we can measure. So just like the periodic table, we've gone through, nuclear physicists have gone through, looked at the energy coming out, mapped them all, etc., etc. We can look at that idea of how much has come out, and we can plot it as a graph. So if we take the example above, so the helium nuclei, then the binding energy is just simply E equals delta M C squared. Okay, so all we're looking at here, we're not looking at the idea of light behind it, we're just using that as a multiplying factor. So if we take that, we've got our 0.048 times 10 to the minus 27 times by 3 times 10 to the 8. Don't forget to square that, so that's 9 times 10 to the 16. What we'll end up with is around about 4.32 times 10 to the minus 12 joules, which is actually quite big for one atom. Okay, that's quite a lot of energy. It's, you know, it's excuse me, it's picojoules, so it's not ridiculously small. However, a lot of our questions, why? Because real life is much easier to use easy numbers, will often use the idea of electron volts. So again, just underneath in your data book, just underneath that, you've got your conversion there. So if we take that, look at the number, 10 to the minus 19, so that was 10 to the minus 12, that's quite a lot of energy on the electron volt scale. Okay, so let's put it in. So I'm going to use the W equals QV, just because that makes it often more convenient. What is that voltage in terms of visualization more convenient? Well, we take our 4.32 times 10 to the minus 12 and we put it over 1.60 times 10 to the minus 19. What you'll end up with is 27 mega electron volts. Okay, that's about 1,000 times more than the energy in light and things like that. So when we were looking at energy levels, again, these are big, so just like we looked at last time. So again, in terms of what's going on here, what we can say is we can convert it. So this is a kind of a more of a background idea where the convenient value is. So binding energy of that would be, from using my example, just squeezed in up here, okay, 0.029 times by 931.3 would equal, obviously, the same number. And I've included that because notice that's so much easier. The conversions, if you have it, if they're given it to you in terms of mass in unified mass units, atomic mass units, all you need to do is take that mass and convert it by the multiplying factor to get energy. Okay. However, expect most of them to be there. So it's a two-step process. Finds the missing mass, okay, subtracts the mass of the individual particles from the mass of the nucleus that you had in the first place, and what you'll find is when you multiply by c squared, you'll get the energy stored up within that nucleus. Now, notice one important thing here. This is the energy to release all of them, to separate all of the particles with the nucleus. Now, often that doesn't happen. We just split a bit off. So what we tend to do is try to get away from this idea of how much energy between each one and look at the idea of energy there. Now, to do that, we're basically finding the average, and we end up with a graph. So the binding energy graph is really famous. A lot of nuclear physicists don't use this, but quite a few exam boards, in fact all exam boards bar one, will use this. OCR B course does the way that most people use it in the nuclear industry. But we'll look at some convenient bits here. Now, notice this is not binding energy. If I put nucleon number against binding energy, I'll clarify what I mean in a second. If we do that, okay, so there's my A number. Okay, so again, that is the number of nucleons. Okay, so that's the big number. Uranium 238, for example, or get that into focus. 238, or carbon 12. You know, lithium 7, whatever it may be. So it's the big number. And if we just put the binding energy, then what we'd get is something that just goes up. Okay, because the bigger the nucleus, the more blue tack in my model, holding it all together. So the more you've got binding, the more energy you're going to release. So it doesn't really tell us much. However, if we divide this value of energy by how many particles are actually separating, we get a much clearer picture. So please notice, this is the binding energy per nucleon. Okay, so the energy divided by the number of particles within it. So effectively, this is the energy needed to release one nucleon. So for example, to pull a neutron out, that's how much energy you would need. And it all depends on the element itself. Okay, and you end up with this beautiful curve. And the curve peaks at around about 56-ish, because there's different isotopes, so it's around about 56-ish. It peaks at iron, and that's really important for a lot of our cosmology stuff. Okay, so we'll come back to that and make that link in a second. However, notice helium has a great big spike here. There's a few spikes. Oxygen is another one, for example. But helium is an incredibly stable nucleus because of the fact that it is, if we clear that out of the way, you know, so tightly bound together, because you can get them so close, and because of them being in that triangle, they're very, very physically stable. Well, because of that, they're also very close together, which makes them nuclearly stable. That's not a word, but in terms of the nuclear properties, it makes them stable as well. Okay, so that means that you end up with a really big spike. You need a lot of energy to take one of the nucleons out of it. Now, if you wanted to find the energy needed to release, we've done it the long way, but if you started at the graph, well, you take the value, that's around about 7, okay, by the look of it, 7 and a bit. That's per nucleon. So if you multiply that by 4, because there's 4 particles in it, 7 4s are 28, 27. There we go. So exact value, but you can get it off the graph. All you need to do is multiply it up by the number of nucleons in it. Okay, so that's a crucial little bit. You may be asked to sketch this kind of idea. So again, some few useful points. So iron, 56, worth pointing out, 56. And that value there, that peak, is 8.8. Just a bit under 9. They won't want that level of detail, but if they were to ask questions like this, and you have a rough idea, you know, up to about 9. Okay, but it's peaking there very, very rapidly at the beginning. Okay, very big increase here, and this is crucial to our next stages, and then more gently. Now, In the video, it's much more like we see in most calculations. They talk about the nuclear valley. So here is a picture of my nuclear valley. This effectively is the graph upside down. Okay, so if I just wait that a second, let's take that graph and turn it upside down. Unfortunately, the picture is back to front, but let's not worry about that. So, if I was to plot that, I'm not going to worry about alpha. What we're going to end up with is a starting value that's quite high, drops down very rapidly, flattens off about 56, and then slowly starts to go up. Okay. What this graph is our nuclear valley. We originally looked at the idea of three-dimensional, so if this is the number of nucleons and this is the number of protons, we ended up with our curve. So if we were looking down on this three-dimensionally, it curved from our same number of neutrons and protons line. Okay, so that was what we were doing last chapter. But what it's doing is all about falling downhill. Okay, so that's why they use the idea of the nuclear valley. So we've got a very tall, very steep section at the beginning, and a more gradual one at the end. Hence this. So think of being in the mountains. Okay, I do regularly. So here we have one of the tarns in the Lake District called Angle Tarn, and what we've got in the bottom here is the most stable version. Okay, so actually this graph is a graph of stability, nuclear stability. So this has the lowest potential energy within it. These have quite a lot of potential energy. Okay, so that's kind of the idea, how much energy they could release. So what are we talking about? We're using a gravitational analogy here. Rocks that come up from our Fermi cliffs, as they're known in our model, our cliffs at the top, well, they are the really small particles. They fall down quite rapidly. If a rock was to break off here or tumble down, what would happen is it would fall down, it smash up into smaller and smaller pieces, it falls a long way down. So it comes down very rapidly, very high speed, a lot of energy released, smashing rocks apart. Okay, that is this idea that if you were to fall from here to here, you'd lose, get the right pen, if you were to fall from say here to here, you'd actually have quite a big change in energy per nucleon. Okay, so for each particle to fall down here, what you'd end up with is quite a big energy being released. At this end, we have a much more gradual process. So, just like the rocks dotted around here, we've got big rocks, much more massive. Okay, these ones tend to be much smaller anyway, the ones that fall off the cliff, but the ones over here got much more massive rocks. They also will fall by the laws of entropy, laws of physics, and they will fall eventually into the most stable area, which is going to be the lake, the bottom of the lake. And they're not going to fall quickly. Okay, rocks aren't going to tumble down, they're just going to slide slowly as Earth is eroded and the whole thing falls gently or slides gently towards the bottom of the hill. Okay, so this much slower process has a much more gradual change in energy, because it doesn't, which is why it doesn't fall rapidly. You don't see them because it takes a lot of energy to move them sideways compared to down in the rocks. But the nucleus, yeah, if it's going down at this lower end, these bigger particles, they move much more slowly. To lose a lot of energy, to release the same amount of energy, you have to move from way up here to way down here. Okay, so actually it doesn't release much energy to get one particle from the nucleus. However, these are bigger nuclei. So again, you're multiplying by the number of particles within it. So actually, how much energy released depends on the process. One of them is nuclear fission, one of them is nuclear fusion, and that's all to do with the process of how to get to this most stable version, which is iron, or as they often call it, iron lake. So if you imagine this as a lake of iron, this is our biggest, most stable area of nuclei, which is why when we have processes in stars and they split apart, so this end here is our fusion process, as stars collapse, our hydrogen, which will be around here somewhere, okay, down on very small numbers, turn into eventually helium and keep getting bigger and bigger. If we can force the nucleons close enough together, if there's enough gravity in the star to crush them up, we'll actually fall into more and more stable isotopes as they become more and more like iron. When they get to iron, okay, they're giving out energy, so the star collapses, it's still emitting energy. That collapse causes it to glow again and give out more light energy out into space. That collapse is giving us energy. However, when we're at the bottom, we would need to put energy in to keep getting bigger and bigger. So to make our nucleus larger and larger and larger, we get to a point where it's not going to happen. So in nature, it's very difficult to go beyond, or rather it takes a lot of energy to go beyond very stable iron isotopes. It does happen, black holes, but that's a monstrous amount of energy. That takes us further up here. But most stars, when they're collapsing, don't have anywhere near enough that energy. Okay, certainly not at this point in space. Nearer, back in time, nearer the start of space, nearer the start of the Big Bang, there was a lot more condensed energy, space was smaller, much more higher energy density, and that's when black holes started to really being formed. You know, that's where most of our space that we see now was formed, when there was much more energy. But yeah, it's all about releasing that excess energy, and that's why most nuclear physicists will use this graph, because it's all about falling down and giving out that energy as our nucleons tumble down the hill, okay, whichever way, slowly or quickly, they're going to give out that energy. And again, worth pointing out, that's the process top and bottom on our graph. So our graph is a section through here. Don't forget they can fall sideways as well. So beta decays, beta plus, beta minus, falling down the hill sideways into the bottom. Okay, so the process happens all the way along as well. But it's all about losing energy. It's all about going downhill. So that's why most nuclear physicists use it, but we will use this upside down. So perhaps this is the energy being bound by each nucleus. Maybe think of this as the energy needed to unbind the graph, okay, unbinds the nucleons. So again, it's often confusing to a lot of A-level students. Think of this as unbinding energy. Right guys, hope that brings that all together quite clearly. Again, don't forget it's all about the proton to neutron ratio as well, okay, from our last chapter, but it's all about that excess energy. Okay, and that's why we have the nuclear valley. Okay, thanks very much. We'll look at the process in more detail in terms of what we're talking with fission and fusion in the next section.